Okay, this video is the second video of fatty acid synthesis entitled Fatty Acid Synthesis 2. Now recall we are in the liver in a fed state with insulin signaling because of the high glucose levels in our blood. In the last video we saw the delivery of substrate into the cytoplasm for fatty acid synthesis. And the delivery of the substrate is in the form of citrate to generate acetyl-CoA. So the 2-carbon building block of a fatty acid is being transported from the TCA cycle through citrate. Now once we have the acetyl-CoA in the cytoplasm, we need to convert it into the next step of the substrate needed for fatty acid synthesis, and that is converting acetyl-CoA into malonyl-CoA. Let me draw these structures so you can see what they look like. So what we've essentially done is on the methyl carbon of acetyl-CoA, we have added a carbon dioxide. This particular enzyme is called acetyl-CoA carboxylase. This enzyme requires a cofactor, the vitamin biotin. Something that you will see repeatedly in carboxylation reactions is that these are one-carbon transfers. So we're going to be adding a carbon to a substrate, or the reverse reaction to remove a carbon in the form of CO2 is always going to require the cofactor biotin. Now also recall that this is a high energy bond. This is going to be taking energy to do this reaction, and so we are going to be using ATP in this reaction. Of course, we can afford to use ATP because we are in a fed anabolic state. Now, important regulatory step of this particular enzyme is insulin. So insulin does not have a very large effect on the liver, but at this particular point, insulin does have a large effect. This particular enzyme will be subjected to becoming either active or inactive based on insulin signaling. So under the case of insulin signaling, the insulin is going to activate a phosphatase. The phosphatase, of course, will remove an inorganic phosphate. Once this happens, the acetyl-CoA carboxylase enzyme will become active from the inactive state. So this means that the inactive state must be phosphorylated. It becomes phosphorylated because of a kinase reaction. The kinase, of course, will add phosphate using ATP as a substrate, and this kinase enzyme is activated by glucagon signaling. Now glucagon, of course, is the hormone signal in the fasting state. So when we are in a fasting state, we want to phosphorylate the acetyl-CoA carboxylase in order to inactivate it, because we do not want to convert acetyl-CoA to its malonyl-CoA. essentially we do not want to make fatty acids in a catabolic state. So we need to shut this enzyme off. During the fed state, the opposite is true. We want to take our excess acetyl-CoA, convert it to malonyl-CoA to make fatty acids. And so now we want to take the inactive form of the acetyl-CoA carboxylase that performs this reaction, and we want to activate it. And the activation sequence is activating a phosphatase by insulin signaling to release the inorganic phosphate and convert the enzyme from the inactive to active state. So both insulin and glucagon control the activity of this enzyme, which is the committed step into fatty acid synthesis. Now the next step is now we have malonyl-CoA. Now we are going to perform our series of reactions to generate a fatty acid. So what we have to look at now is a very large molecular complex, which is called the fatty acid synthesis complex. This complex is a collection of a large number of enzymes and structural proteins. The complex itself will be performing all of the reactions necessary for generating a fatty acid from our precursors. So therefore, the official name of the complex is the fatty acid synthase complex, reflecting the need for an enzyme, ASE. So now the first step of this reaction is we are going to have what is called an acyl carrier protein, abbreviated P. Acyl carrier protein. Now recall, these are all individual proteins within this large fatty acid synthase complex. We also have another protein that will be contributing a free sulfhydryl. And it's these two sites on the fatty acid synthase complex that is going to be mediating the reactions necessary to elongate the long hydrocarbon chain of a fatty acid. So the first reaction we're going to perform is to take the molecule acetyl-CoA prior to its generation of malonyl-CoA, and we are going to hydrolyze the thiol ester bond to couple this acetyl group to the P site. And of course, we will be releasing CoAsh in this reaction. So it's the thiol ester linkage that is driving this reaction to couple it to the acyl carrier protein site. The next reaction is going to move this complex over to the free sulfhydryl. So we are simply shifting the acetyl group located on the P site to the sulfhydryl on the next protein, leaving the P site open. Now, the next reaction is going to be taking malonyl-CoA, and we are going to add this malonyl-CoA onto the P site that is now available for binding. Here's our malonyl-CoA. And of course, we're releasing the coenzyme A group that's associated with malonyl-CoA. Now, the next step of this reaction is what is called a condensation reaction. So we are essentially going to take this carbon and attach it to this carbonyl of the acetyl group located on this thiol bond. What that will give us is this structure. Now notice what we've done is we've taken 2 carbons of the malonyl group and added it to the 2 carbons of the acetyl group. By doing that, we've lengthened the chain now to 4 carbons. Now what happened to this CO2? This CO2 left during this condensation reaction to release the energy needed to perform this condensation reaction. Now, this first reaction defines exactly how the fatty acid is going to be made. Recall that our fatty acids are generally even numbers, and so we are going to be adding 2 carbon units to lengthen the chain of hydrocarbons to generate ultimately our even-numbered fatty acid hydrocarbon chain. Our longest one that we generally make is C16. So now once we have this structure, we are going to perform a series of reactions in order to process this carbonyl to make it a hydrocarbon. Now that I look back on here, my apologies, this is actually on here. I was thinking too far ahead. So let me put this into the correct state. This will be on the acyl carrier protein. This is, of course, free. Here's the mistake I made here. This is a condensation reaction. We're adding these acetyl group here onto this carbon here, which remains on the acyl carrier protein. Minor issue, but let's keep the stoichiometry correct. Now, let's perform the next reactions in order to process this carbonyl. So I will keep this correctly on the P site. And what we have in the next step is to begin processing that carbonyl. And what we are going to do is convert this to an alcohol. Now, whenever we convert a carbonyl, a ketone, into an alcohol, recall what kind of reaction this is. This is a reduction reaction. So we perform a condensation and a reduction reaction. Now, where are these electrons coming from to perform this reducing reaction? Here is where we're starting to use some of our NADPH that we generated. Now the next step of this reaction is going to be simply a dehydration reaction. In performing this dehydration reaction, we are removing water from the two center carbons to generate a double bond. Now that we have a double bond, all we have to simply do is perform one more redox reaction. Let's draw this on the next page. And we will have our hydrocarbon chain. Let me just draw this out. So we have our double bonded molecule. So here's our double bond. We just need to reduce this double bond. And in reducing that double bond, we generate this molecule. Now, being a reduction reaction, we're going to need a partner that is performing the reduction. And again, this is where we'll be using more of our NADPH. So now, once we reach this state, notice what we've generated. We've got a carbonyl, and we have a fully saturated carbon chain. What we have here is actually considered a C4 0 fatty acid. So now we've added essentially two acetyl groups together to generate our hydrocarbon chain fatty acid. Now the next step is to move this fatty acid chain over to this sulfhydryl group. That will leave this sulfur open on the acyl carrier protein. So the next step here, again, is to add malonyl, CoA. So once we add our malonyl CoA, now we can perform our next reaction. The next reaction will be this carbon attaching in a condensation reaction to this carbonyl. Notice what we've added here. Here's our 4 carbon that we started with. Here's our acetyl group we added. And once again, we've now added 2 more carbons, and now we have a C6 carbon chain. The next step, of course, is to transfer this to the sulfhydryl group. After we perform our chemistry, and recall the chemistry of the reactions, we just performed a condensation reaction. Now we will perform a reduction, a dehydration, followed by a final reduction. And all of these reactions will be performed on this carbon. What we will generate in the end of this round of reactions is to have our carbons on the sulfhydryl group with the peace site available for the next reaction of malonyl. So at this point here, we have a fully saturated C6 fatty acid chain. Again, the next round, we perform condensation reaction, and we're going to add 2 more carbons to generate a C8. Now we do this reaction multiple times, continuing around the cycle, until we are going to generate a C16 0. This is called palmitate. This is the fatty acid that we generate on the fatty acid synthase complex. Now, in order to release this fatty acid from the complex itself, we will add, in the end, coenzyme A to displace off of the sulfhydryl group the fatty acid in the form of a fatty acyl CoA. (16) will be 1, 2, and 14 CH2s. By releasing the fatty acid from the fatty acid synthase complex using CoA, we have now introduced a high energy bond. This fatty acid now will be used for storage of fatty acids. Ultimately, this will be delivered to adipose. We'll look at this delivery method in a separate video. Now, the one more piece of information here is that once we generate this fatty acyl CoA, what would prevent this from entering the mitochondria and being subject to beta oxidation? Picture if this happened. We would have our acetyl-CoAs coming down the pipe from glycolysis and the pyruvate dehydrogenase reactions being delivered to the cytoplasm, being used in these repeated rounds of fatty acid synthesis so that we generate a large fatty acid molecule, C16, only to turn around to deliver it into the mitochondria by the carnitine shuttle. Recall that the carnitine shuttle is going to convert the fatty acyl CoA into fatty acyl carnitine, and then that will be translocated in the mitochondria and then regenerate the fatty acyl CoA to be put into beta oxidation. The result of that is acetyl-CoA. If that happened, we would be right back to the starting point, but using all of this energy in a futile way. This is a futile loop. And so in order to prevent this from happening, recall that we have our acetyl-CoA carboxylase enzyme that is converting our acetyl-CoA to malonyl-CoA. So recall, this is our first step in generating our substrate for fatty acid synthesis. Malonyl-CoA is in the cytoplasm, and this will inhibit CPT1, which is the carnitine palmitoyl transferase 1. So the enzyme responsible for fatty acyl CoA to make the fatty acyl carnitine for translocation into the mitochondria, that enzyme is CPT1. Malonyl-CoA inhibits this enzyme. So as we have acetyl-CoA building up in the cytoplasm for fatty acid synthesis, this is converted into malonyl-CoA. The malonyl-CoA is used for fatty acid synthesis, attaching onto the acyl protein site. And in addition, it's also inhibiting CPT1 to prevent the fatty acyl-CoA conversion to fatty acyl carnitine to be translocated back into the mitochondria. So what that essentially does is it prevents the fatty acyl-CoA from entering any other pathway except storage. And the storage is going to be in the form of triglyceride synthesis. And these triglycerides will be transported to adipose tissue. We'll take a look at that process in another video.